ahead and start. So this is Intro to CIS 1. This is the first exposure that most of you are going to get to this department. And if right now you're feeling a little apprehensive because you don't think that you have very much programming experience, realize that most of your peers don't either. Historically, we found that 70% of people who come into this class and start have almost no prior programming or CS experience. So I'm curious for this version now. Raise your hand if you've had some amount of coding. You've coded in some language, Java, Basic, C++. It's about half of you. Now, I'm actually taking two sections of this. So there's, this is maybe 1/4 of the actual class. So it seems about 50-50 for this class. I'm sure once I go into the bigger lecture hall, it'll be even less. So generally, it winds up being about 70. And, okay, good. That's not a major problem. So don't feel too bad if you're not entirely sure what you're doing or wondering why you're here, because we're going to assume that you have a blank slate. In fact, some of you that do have programming experience might be at a slight disadvantage because you may have picked up bad programming habits along the way that we're going to have to kick. So much of this course is going to be about learning computer science as well as the art of programming, how to make you guys really, really good programmers. So we'll start with something simple, though. How do you usually interface with your computer to the world of electricity through a power cable, right? So what is this power cable really feeding into your computer? It's feeding electricity. And so what is a computer really? It's really a way of storing electricity and utilizing what we call transistors to turn basically a lot of little buttons on and off to create information. And what makes them so amazing is that you can take a lot of very simple functionality, which really transistors are just on and off buttons. If you have electricity flowing through, that's considered on. If it's not flowing through a transistor, it's considered off. And from using lots and lots of these little transistors, you can build up the entire world of computation sort of as we know it. So the first thing that we're going to touch on is binary. So a simple on and off switch, essentially. And I assume now in this sort of age of computation, as people are now becoming more and more familiar with computers, most people have heard about binary in some form or another. It's really just literally an on or an off switch. And what computers can do is map these into numbers. So, for example, right now, not by doing anything, I'm going to be representing the number 0. And if I have a flashlight, I can turn a light on, and now I'll be representing the number 1. And so if it's off, that's the number 0, and if it's on, that's the number 1. This is all well and good, but the power really comes when we combine more than one together. So now if I have an additional light source, I can represent twice as many configurations. Now I can represent 4 configurations instead of the 2 that I had prior. So I can have everything off and be representing 0, representing 1 like I had before. But now I can turn this additional light on and have 3. Well, so, okay, 0, 1, this would be 2, and then having them both on would be 3. And so that's a total of 4 configurations, 0, 1, 2, and 3. One thing you guys will have to get used to doing is counting from 0 in this course, which takes a little bit of practice, and sometimes I forget it as well. But so the real power is that when you combine a lot of these together, they build up exponentially. So if I have 1 bit, a binary digit as it's called, I can represent 2 possibilities. 2 bits can represent 4 possibilities. 3 bits, 8, 16, 32, etc. And so using just 5 bits, you can represent 32, 6 bits, 64, and it continues ad nauseum. And so this is really powerful because you can use a relatively small number of bits to represent a lot of information. And since computers hold a large number of bits, there is a lot of information that can be represented. And so that's all well and good. We can represent numbers, but then you can start to build on top of that by using numbers and mapping them into letters. And so we use the ASCII system to do that. So your computer, when you type a key into a keyboard, is really receiving a number, and it's converting that using this ASCII system into a letter. And so there are 120 total ASCII characters. They represent letters as well as uppercase, lowercase, punctuation, some special symbols. So this portion from 65 to 90 represents a certain subset of capital letters. And so you can map these numbers into letters and start to build up a whole wealth of important word applications. You can get sentences and paragraphs and whole emails now just from numbers, which were originally represented in binary, which themselves have the representation as transistors in the computer. So once we are done with words, we can move on to images. So how would one represent an image in a computer? Well, you can do it the same way by using a binary system. So this is a simple binary image. It has a number of pixels, and each pixel can have sort of a switch associated with it. It can either be on, and it can be black, or it can be off, and it can be white. And so once you have a lot of these pixels, or a lot of these sort of bits together, you can compose them into a picture. And if you zoomed in, I don't think I have zooming functionality here, but you may be able to make out that all of these are really just tiny, tiny little dots. They can be either on or off. But then how do we generate more richer pictures than we have here? Well, you can, instead of associating a single bit with a pixel, you can associate 2 bits with a pixel. If I associate 2 bits with a pixel, then I have 4 states that each pixel could be in. So I might be able to have white as the 0th state, and then 3 would be the black state, and then in between I might be able to have a range of various grays. And so this would be a 2-bit image, and you can see compared to the 1-bit image, it's just a little bit more rich because it's got a wider wealth of grays. And I could, again, continue this process further by, instead of going from a 2-bit image to a 3-bit image, which has how many different possible combinations? Or how many different states for each pixel? 8. And then the 4-bit image, which has 16 different states. So this would be 16 different shades of gray that each pixel could take, and now you finally get images which are a little bit more realistic looking. And when you want to add color, that is its own beast. And so the way that we usually do that is we use the RGB system, which means red, green, and blue. Most common systems have a 24-bit RGB system. So what this means is that at each pixel, you'll have 8 bits of red, 8 bits of blue, and 8 bits of green. And 8 bits means that you can have 64 different color schemes throughout there. With 2 to the 8th. Sorry, no, 8 bit is 255. 256 total, 0 to 255. So there's 255 different shades of red, green, and blue associated with each pixel. And so you can build up a large range of very colorful, very vivid images, using, again, just simple bits. And so that's really going to be the theme of this course, is that we're going to take very simple things, starting from simple bits, and build them up to be a whole wide range of interesting and useful applications. So again, this is Intro to CIS 1. And so in Intro to CIS 1, we're going to talk about really problem solving at its core. This is not entirely a programming course. You will learn to program, and you'll learn to program hopefully really well, but the ultimate goal is to not necessarily learn programming solely as a means to an end. It's really the art of problem solving using algorithms and using computation. And so that's really what our goal is going to be in this course. So we've talked about how computers can store information using bits. Now we'll talk about how we can actually get them to do things. And so as a very simple example, let's say that I wanted to look up a name in a phone book. So what could I do to look up that name? I could start at page 1, and I could flip through one at a time. So let's say I wanted to look for Mike Smith in the phone book, let's say. I could look through the phone book one page at a time and check, okay, is that in the phone book? No. Or is this Mike Smith? No. Next page. No, still not Mike Smith. Next page. And this is a correct algorithm. This would eventually, over a matter of time, get you to Mike Smith, but it's not really an ideal algorithm. So what would you do? How would you try to find this name in the phone book? You'd probably open it up halfway, and you'd look, okay, I'm in the M's, let's say. I'm halfway through the alphabet. Well, I'm looking for Mike Smith, so it'd be in the S's. So I know that it's probably not in this left half portion, or I guess in your case, right half portion of the phone book. It's probably only in this portion. And so I can essentially remove from my mind the entire left-hand portion of the phone book and repeat the same process using a much smaller portion of only the right-hand portion that I had. So now I would have something that's only the M's to the Z's, and I could repeat the same process. I actually wanted to use this using a physical phone book, but I realized I don't have a phone book in my house, and I couldn't find one in this department. It shows you that this is sort of the age that we're going in right now, that we're completely doing away with phone books, and it makes some of these examples a little more difficult. But so if I'm looking for Mike Smith, I might now have a section of the phone book that has only M's and Z's, and I might open that part up halfway and say, okay, now I'm in the T's, let's say, and I could remove everything from T to Z. And so by periodically opening up my phone book in each step, I could whittle down eventually to the one page that I want. And this is what we computer programmers call binary search. You are cutting the program in half, essentially, every single time that you take one of these steps. And so this is a very simple algorithm, and one of the themes of this course that we'll be doing, which will be taking simple things and building them up to more complex things. So the first algorithm that I talked about, this sort of linear one of sort of paging through one page at a time, this is what we would call a linear algorithm. So I would go one page at a time, and depending on how big my phone book is, it takes that many steps sort of to complete. I could take this one step further, and I could look maybe 2 pages at a time. And so rather than going at only one page, I would, in a sense, double my speed through the process. And this is good too, but it's still linear. It still increases. If the phone book increases in size by, let's say it doubles in size, that's still a large number of pages that I have to sift through. The binary search algorithm that we were talking about prior to this, or just now, is what we call logarithmic time. And so that's really nice, because if the phone book doubles in size, let's say it was originally 1,000 pages, and then it goes to 2,000 pages, how many additional steps does that take? Just one. Because if I open the 2,000-page phone book up halfway, and I cut the program into either the algorithm into either the left side or the right side, I've now reduced it to only 1,000 pages, which is what my original program was. So binary search is very, very powerful, and logarithmic time algorithms in general are very, very powerful. And we can see that by learning to think sort of algorithmically and thinking like a computer scientist, we can do things much, much faster than we might have already thought. But not just faster because computers themselves are inherently fast, but learning to actually take problems and solve them efficiently and optimally using algorithms. Any questions now before I continue further? So, what I want to do is show you guys a video on algorithms, which I thought was really, really nice as sort of an intro to algorithmic thinking.
What's an algorithm? In computer science, an algorithm is a set of instructions for solving some problem, step by step. Typically, algorithms are executed by computers, but humans have algorithms as well. For instance, how would you go about counting the number of people in a room? Well, if you're like me, you'd probably point at each person, one at a time, and count up from 0. 1, 2, 3, 4, and so forth. Well, that's an algorithm. In fact, let's try to express it a bit more formally in pseudocode. English-like syntax that resembles a programming language. Let n equal 0. For each person in room, set n equal to n plus 1. How to interpret this pseudocode? Well, line 1 declares, so to speak, a variable called n and initializes its value to 0. This just means that at the beginning of our algorithm, the thing with which we're counting has a value of 0. After all, before we start counting, we haven't counted anything yet. Calling this variable n is just a convention. I could have called it most anything. Now, line 2 marks the start of a loop, a sequence of steps that will repeat some number of times. So in our example, the step we're taking is counting people in the room. Beneath line 2 is line 3, which describes exactly how we'll go about counting. The indentation implies that it's line 3 that will repeat. So what the pseudocode is saying is that after starting at 0, for each person in the room, we'll increase n by 1. Now, is this algorithm correct? Well, let's bang on it a bit. Does it work if there are 2 people in the room? Let's see. In line 1, we initialize n to 0. For each of these 2 people, we then increment n by 1. So on the first trip through the loop, we update n from 0 to 1. On the second trip through that same loop, we update n from 1 to 2. And so, by this algorithm's n is 2, which indeed matches the number of people in the room. So far, so good. How about a corner case, though? Suppose that there are 0 people in the room, besides me doing the counting. In line 1, we again initialize n to 0. This time, though, line 3 doesn't execute at all, since there isn't a person in the room, and so n remains 0, which indeed matches the number of people in the room. Pretty simple, right? But counting people one at a time is pretty inefficient, too, no? Surely we can do better. Why not count 2 people at a time? Instead of counting 1, 2, 3, 4, 5, 6, 7, 8, and so forth, why not count 2, 4, 6, 8, and so on? It even sounds faster, and it surely is. Let's express this optimization in pseudocode. Let n equal 0 for each pair of people in the room. Set n equals to n plus 2. Pretty simple change, right? Rather than count people one at a time, we instead count them two at a time. This algorithm is just twice as fast as the last. But is it correct? Let's see. Does it work if there are two people in the room? In line 1, we initialize n to 0. For that one pair of people, we then increment n by 2. And so by this algorithm's end, n is 2, which indeed matches the number of people in the room. Suppose next that there are 0 people in the room. In line 1, we initialize n to 0. As before, line 3 doesn't execute at all since there aren't any pairs of people in the room. And so n remains 0, which indeed matches the number of people in the room. But what if there are 3 people in the room? How does this algorithm fare? Let's see. In line 1, we initialize n to 0. For a pair of those people, we then increment n by 2. But then what? There isn't another full pair of people in the room, so line 2 no longer applies. And so by this algorithm's end, n is still 2, which isn't correct. Indeed, this algorithm is said to be buggy because it has a mistake. Let's regress with some new pseudocode. Let n equal 0. For each pair of people in the room, set n equal to n plus 2. If one person remains unpaired, set n equal to n plus 1. To solve this particular problem, we've introduced in line 4 a condition, otherwise known as a branch, that only executes if there's one person we could not pair with another. And so now, whether there's 1 or 3 or any odd number of people in the room, this algorithm will now count them. Can we do even better? Well, we could count in 3s or 4s or even 5s and 10s. Beyond that, it's going to get a little bit difficult to point. At the end of the day, whether executed by computers or humans, algorithms are just a set of instructions with which to solve problems. These were just 3. What problem would you solve with an algorithm?
Alright, so that's all nice and well. That is, go to the beginning. So that was the basics of sort of what an algorithm is. So an algorithm is essentially a step-by-step set of instructions for how to do things. And that was sort of an intro into how to count people using for loops, using if-then conditions, things that we're going to see a bit more of as we get more into the course. So was that a linear algorithm or a logarithmic algorithm that he was using to count? It was linear. He was only counting 1 at a time, maybe at most 2 at a time. So is there a way that we could solve this problem using maybe a logarithmic way of doing things? I would posit that there is. And so I'm hoping that you guys will kind of indulge me in a nice, fun little experiment. And everybody stand up. So you're going to start with the number 1. Yourself, and then you're going to pair off with somebody else. You're going to add your 2 numbers together, and then since I need some way to break the tie, the shorter of you will sit down, and then you're going to keep doing that. So 1 is going to add to 1 to get 2, 2 is hopefully going to add to 2 to get 4, and then hopefully within a very small number of steps, we'll get to the total size of the classroom in a much quicker fashion than if I had gone 1, 2, 3, etc. So execute. I know this is a little bit awkward, but you're getting to know your fellow CIS 1 friends and brethren. People have sat down. All right, so who hasn't been paired off yet? Raise your hand, I guess, if you're still standing. Okay. Hold on. Okay, so how many people did you end up with? Are you sitting down now? Okay, so I guess we're down to 2. How many did you end up with? 39. And you got 23. And that's it. So 23 plus 39 is what, 62? So there are supposed to be 85 people registered for this course, which means that we have a bunch of people absent. But we got relatively close to the number, and so we certainly got to the wrong number a lot quicker than had I just started and gone 1, 2, 3, 4, etc. So this is sort of a nice introduction to also another good aspect of computers, which is parallel processing. You guys were able to execute a lot of different branches of computation simultaneously because each one of you was your own little thread or your own little sort of processor that was going on. So that was sort of an introduction to an algorithm. And into pseudocode, which is sort of a set of steps for executing a certain operation. In this case, I made you guys all the computer. I had a set of 3 lines for what I wanted you guys to do, and you executed, and you finally banged out a final result. So now we'll look at a little bit more pseudocode in slightly more detail. So pseudocode is itself sort of English-like syntax for illustrating an algorithm, illustrating something that you want to do. So as a start, I'll consider the task of averaging 2 numbers together. So this pseudocode says that I have to input 2 numbers, which I'm going to call N1 and N2. These numbers, N1 and N2, are basically, well, the actual letters, N1 and N2 themselves are variables, just like you might find in math. They're holding specific numbers that they might represent, maybe 45 or 90 or something like that. And so the first thing that I'm going to do is, if you want to compute an average, you have to add those numbers together. So this second line is saying take N1 and N2, which were input, add them together, and then store the result in a new variable that I'm going to call sum. And then after that, what's the next step to taking an average? You have to divide by 2. So I'm going to take sum, so the actual number that is contained in the variable sum, divide it by 2, and then store that in a new variable, which I'm going to call average. And then the final step is maybe to just print the average. And so this is a simple, very, very simple set of instructions, but this is English, and by the end of the week, you guys will be writing actual computer programs that will be able to do something very similar to this, and then obviously on and on to more complex things. But what if I wanted to take the average of 3 numbers instead of just 2 numbers? How would I have to change the program? I'd have to add an extra line, which is the third line there, which says, well, okay, I added the first 2 numbers and stored them in sum. Now I have to take the third number as well, add that into sum, and then divide the result by 3 as opposed to just 2, and finally print the average. And so this is correct, but as we have more and more numbers, we'll be able to find that the number of lines can really get very long and very tedious. And so we have a construct as computer programmers that we can use that we call a for loop. So this is saying something that's going to iterate many times over. So I'm going to start with the variable sum and set it to 0 because there aren't any numbers. And let's say now I have a set of numbers, which I'm going to call n. This is a giant bag that contains many numbers. And then for each number in the bag, I can imagine almost pulling numbers out of the bag. And each time I pull a number out of the bag, I'm going to call it little n. And I'm going to do things with it, and I'm going to refer to it by that little n label. And so for each little n in n, take my sum, take my counter, add n to it, and repeat until the bag is empty, until there are no more numbers left. Off you go. So I'm using a little indentation to show you things that are happening inside of the for loop. And this is a programming style tip that you guys will be using, which is that when you have loops, the things that are happening inside of the loops will usually be indented to show you, sort of when you immediately look at the program, you can tell which processes are being repeated over and over again. And so after I've got a really large number, which is my sum, I'm going to, in the penultimate line, do something which is called a function. I'm going to apply something to this n, to this bag of numbers that I originally had, to figure out what the size was. And this size with n parentheses is going to return back a result to me, which is going to tell me how many numbers I had to begin with. And so I can add up all of these numbers with a big for loop, divide by the size of the original bag that I had to begin with, and then store that result in average and print it out. And so this is your very first introduction to for loops, which we will be using very, very, very much throughout this course. The second major construct that we're going to talk about is ifs and thens, or ifs and elses. Sort of if something happens, if I want something to happen, I have to check if this condition is true, and if it is, then do this thing. And this is the way you can have sort of program flow. I can have many different options for my program to take. I can say if this condition is true, then do this thing. So let's say that I'm computing grade averages, and I'm going to print out whether this person is a good student or they're spending too much time on Facebook. I can do some of the things that we talked about before for computing the average. So I take all the numbers in the bag, I add them all together, I divide by the sum, and then I have this final result average. And I look, well, if the average is greater than 80, then maybe I want to print good job and give them a little bit of validation. Otherwise, I want to tell them, okay, you're spending a little bit of too much time on things like Facebook. Maybe you should do a little bit more studying. So the clause that appears after the if is what we call a condition, and it takes a Boolean result. And I'm throwing out a lot of terms to sort of expose you to these things, but we're going to come back to them in greater detail throughout the course. A Boolean phrase can take a true or a false. And so if this if statement has a Boolean value which is true, then it executes what's directly underneath it. Otherwise, if it's not true, it executes what's underneath the else statement. And so this is just a very short introduction into how computers store information through bits and how we get them to do things through algorithms. So now let's talk about sort of the overall structure of this course and how things are going to work. Because this is a bit of an experimental course for me as well, because this is my first time teaching the course. And I'm trying to teach it in sort of a new way. So there's going to be a lot more multimedia included throughout this course, as well as sort of a different way of doing things. So we'll start with the lectures. And you guys are all in the right place, except for maybe 23 of you who seem to be absent. They will be 10:40 on Mondays, Wednesdays, and Fridays. I have an additional section at 11:45 in A101 across the hall. Now, I'm supposed to tell you that you have to come to the section that you're registered for, but sometimes things happen, and maybe you can't make one section. I will allow you to come and sit in on the other sections because they're going to be pretty much the same material throughout both. So feel free to come to either one of the lectures, but if it starts to get out of hand and the second lecture hall is a little bit too crowded, and I'm sure some of you might want to sleep in, I may have to do away with that and force you guys to start coming to this section. For now, you can choose one of them. So in addition to the lectures that I'm going to be giving 3 times a week, there are going to be discussion sections. And so those are going to be on Tuesdays. You should already know through your schedule which room you're registered in. It's usually one of the ones in this floor, either E116, E115, one of those. And that's really time for more one-on-one discussion with, well, not really one-on-one, but a few on-one discussion with the TAs. And so I don't have all of my TAs figured out yet, so I can't bring them up to introduce them, but I'll probably do that on Wednesday or Friday. But you'll be grouped off with a TA during your discussion sections, and you'll have some kind of short assignment to work on throughout the section. Things that will start to acquaint you with the basics of programming. I'm going to give you guys a little bit of introduction to Linux, because that's really the space that most of us should be programming in now if we're all going to be doing computer science as a major. So the discussion sections are really the place for you to ask questions. I mean, you're welcome to do that in the lecture as well, but I can only handle so many things if I have a group of 85 of you. So the discussion section is really a chance to sort of pair off and work on homework assignments, problem sets, things of that nature, under the supervision of a discussion leader who will be helping you as best they can. In addition, we have office hours, and these also aren't decided because I don't yet have all of my TAs, but I will be providing you guys a schedule throughout the week of office hours, which will hopefully be every day and covering most of the hours throughout the day. And so there'll be a specific room that you'll be assigned to that I will also let you know of at a later date. And you can come and get additional help. And that you can get in on an even smaller scale in the discussion sections and have really, hopefully, one-on-one interaction with the TAs, with myself, and for asking us questions and of the sorts. So the sort of structure that this course is going to take is going to be less of, here are all of the things in Java that I want to teach you. Instead, it's more along the lines of, here are all the problems that I want you guys to be able to solve before this course is over with. And so I've kind of partitioned it into 7 sections. And so the introduction is going to be what we're doing today. So we start the very, very basics of what is a computer, how do we store information and get it to do things, how do we do programming at a very, very basic level. And we'll be looking on Wednesday at a graphical programming language known as Scratch. and sort of before we even get to Java, learning the very basics of what it means to program and how to solve problems using programming. And then we're going to progress on to various different data types and how to do cool and interesting things with them, such as numbers. Objects are specifically things appropriate to Java that will make more sense when we get to that. But words, doing natural language processing, creating games, which we will be doing later. And then by the very end, we'll be working with the web, and I'll be teaching you guys a little bit of HTML and JavaScript, and we'll be creating our own web applications as well. So there is no required textbook for this course. And for computer science in general, that should always be the case. There are so many free resources now available that you should not have to pay $120 for a hardbound book. You are more than welcome to if that's what you prefer, but there are many resources that I'm going to make available to you. And so in the syllabus on the website, which I will get to, there are 3 books that we're mainly going to be using as sort of a skeletal guide. Think Java, Introduction to Programming Using Java, and then this Thinking in Java. These are three textbooks which you can download, and they all do a few different things really well. Think Java is a really, really good sort of simple introduction, but not very comprehensive, whereas at the other extreme, Thinking in Java is very, very comprehensive, not necessarily for the beginner. And so I'll be picking and choosing just a few small things that I think it does really well. So we'll sort of use all of these 3 books, and I'll assign various readings, but we'll by no means be looking for a completeness of all 3 of these books. Yes, yes. And so I'll show you guys the website on the very, very last slide. So the main core of this course, though, are going to be the problem set. So as I said, I separated the course into sort of 7 different sections. And there's going to be a problem set associated with each section. 75% of your grade in this course will come from these problem sets because you learn computer science by doing, not by rote memorization, not by memorizing Java syntax, and not by doing well on exams. And so the real boon of this course will be to teach you to be good computer scientists by completing projects. So there will be 7 total, and you'll have late days associated with these projects. So I'm going to give each of you 3 late days that you can spend on each project. So they'll generally be due on either a Saturday or a Wednesday. And if you want, you can take a late day and have an additional 24 hours to work on your assignments. You'll only have 3 of them to spend on the 7 projects, and you can use at most 1 per project. But this is all handled automatically, so it's not something you'll have to worry about or notify us of. But if you wind up taking a little bit of extra time on your assignment, for some projects, that's fine. Going over by 7 minutes is the same as going over by 23 hours. So a day is a day, and you cannot break it up any other way. And so these problem sets will be increasing in both the challenge and the level of skill as we develop more and more of a toolkit for programming, but they'll also increase in worth as well. And so we'll start off with the very, very first programming assignment, which is going to be due next Wednesday, utilizing a language that we're going to talk about on Wednesday, known as Scratch. And then from there, we're going to progress on to a few other interesting projects. Cryptography will be working with numbers and trying to do some elementary code breaking. In Google Maps, you guys are going to design sort of a little, you're going to utilize the object information that you learned about in Java to create sort of a very basic map system in which you'll be able to give it directions and create a little car that can take little routes on a map of Gainesville. The game of 15 will be a game that you guys will develop that will sort of test your graphical know-how, and you'll be exploiting a few libraries in Java to create a rich graphical application. The natural language processing project is going to be a spell checker, so you'll be able to take in a document and scan it for words that might be misspelled by cross-referencing with a dictionary, and maybe do some interesting things in addition to that. Mario will be a platforming game that you guys will develop. And then Twizzler, which will be the final sort of web application, which will be a Twitter-like thing where you can create your own Twizzles and follow people and friend them and whatnot. And we'll see how far we can go with this. As I said, this is the first time we're teaching this, and so a lot of this will adapt as necessary. So I have most of these projects worked out, but they are subject to change, and so all of the information as such should always be referred to on the website, and so this is not necessarily final, but this is the outlook of what I want to present to throughout the class as a whole. In addition, you will have exams, because I'm in some sense required to give a small number of exams to discourage cheating, but they will be small. They will be small in worth, only 10 and 15% of your grade. They'll be roughly distributed about 1/3 of the way through the course. So the first one will be about 1/3 of the way, the second one will be about 2/3 of the way, and there won't be a final, because I want you guys to be working on your web application, and you can't really work on an interesting cool project while also worrying about memorizing things for a final. So these are more or less to sort of act as checkpoints. Okay? When we get to this point, are we all on the same page? Do we all sort of know how to do the same things? And hopefully they'll be relatively low stress, and they won't be concerned with memorizing specifics of syntax, which can frustrate a lot of people. They'll be testing ideas. And so 75% on the projects, if you add all these together, that's what they get, and 25% for the exams. There is not a curve of any kind in this course. You're not competing with anybody in this course. You're competing with yourself. With yourself right now in week 0 versus yourself in week 12 or 13 or whenever we end the semester. And so the hope is that we will start off with a clean slate, not knowing very much, and then throughout the semester get better and better and better. And that is what we're looking for in this course. And I am allowed to give every single person in this course an A. And I want to give every single person in this course an A. And ideally, that's what will happen. And so if we all work hard and are persistent enough, we can all do well. But this will be a hard course. There will be lots of problem sets, as we have seen, and they're going to challenge you. And because of the fact that there aren't really an emphasis on exams and on memorization, I'm going to try to get you guys to do interesting things through the projects. But there will be lots and lots of resources for you guys to take advantage of. Myself in the lectures, as well as the discussion sections, as well as office hours. If I feel the class has fallen behind, I may hold additional tutoring sessions as well, where we'll maybe meet for an additional lecture size thing and maybe go through additional aspects of the problem sets. So this course is really about you trying as hard as you can to do well at the art of programming.
Are we allowed to use the web as a resource for helping us figure out?
Yes. So I am not crass enough to say you're not able to utilize anything. There is a wealth of information on the website. What you may not do is explicitly copy code. But you can use the web as a resource to help yourself, to help teach yourself. We all might find tutorials of certain aspects of code that might help us, and you are welcome to use those as tutorials to help you. Now, I'm hoping to design my projects in such a way that you won't be able to find easy solutions on the web. But some of you might be more resourceful than others. As long as you're not copying and pasting code directly and you're able to elucidate your own ideas through the code, that's what I'm looking for. Question?
Are you going to go over the grading criteria for problem sets, or can you solve them individually or
Yes. So I am going to, as I assign the projects, I'm going to explicitly tell you what I'm looking for in them, but most of them will be, it will depend on the project. So some of them, I will give you guys a skeleton, and you'll code out the guts, basically. And so there will be some room for creativity, but there won't be very much since you'll have the objects there. Then there might be others where I will say, okay, we're starting from a blank slate. Here are all of the ideas, go. And so depending on the project, that might differ. But for the most part, you will be able to solve these how you want to solve them. I'm trying to encourage creativity in the best way that I can. And for each project, there will be some creative aspect that you'll be taking advantage of. For instance, in the Mario game, you'll be designing your own actual level. And so each person will have their own different levels, hopefully, that we'll be utilizing. In the Google Maps and the spell checker, there will be additional features that you may or may not implement at your leisure. And so I may also, for some of these problem sets, assign bonus points for, well, here's something really, really cool. Can you figure out a way to do it? And if you can, I'm willing to give you bonus points. If every person completes the project and does so in a way that can run and does a fair number of interesting features, not even necessarily the bonus features that I assign, and then can do all right on the exams, there's no reason not to earn an A. But as a result of that, I'm going to have to make the projects a little bit challenging. But not challenging from the perspective of you're not going to know what to do. Challenging from a perspective of, well, here are all of the things that we've talked about. Here is how you can use them. Go use them. Go show me that you know how to code. And as we actually assign projects, this will become, you'll become more comfortable with this. But if you're feeling uncomfortable right now because of the wealth of worth that these projects have, I would say don't worry. I am not going to give you a bare one-paragraph spec and say, go create Mario. You will have many, many things, and generally my problem sets will probably be 3, 4, 5 pages in length as I walk you through a lot of the steps necessary to complete the various aspects. Questions? So,
what compiler are we going to use?
Jumping ahead of us. So I'm going to give you guys any choice of compiler if you want. We're going to be using Java, so the Java C compiler will be the standard compiler that they'll use. But I will also allow people who are familiar with using a development environment like Eclipse to use that as well. But it's about 4 days away. By Friday, we'll be getting to actually writing our first Java programs and talking about compilers and all of these things. And so all of this information can be found on the website, which I have been able to acquire, which is cop3502.com. Now you cannot forget it. Right now, it's kind of in an unfinished state. I'm still developing things and adding things to it, but at the very, very minimum, you can go through and access the syllabus. And so if you hit the big green button that says syllabus, then you can see everything that we've talked about already, including the books. There are links to the books on there, and discussing all the various things, the problem sets, as well as tentative due dates for the problem sets, and discussions of exams, grading policy, a list of all the topics that we will be trying to cover. I'm intentionally trying to be ambitious with this course, and so we will move somewhat quickly, but somewhat thoroughly. And I'm willing to adapt as necessary depending on the expectations of the class. And then finally some various things that the university requires me to discuss, including academic honesty and what you may or may not do with regards to communicating with others for help. Any other questions on that regard with the syllabus? Anything that you want to know about this course that I may have not covered yet? If that's it, then like any good first day of class, we are going to finish a little bit early, and I'll let you guys all head out. Wait, there is a question. Someone wants to keep us in. Yeah, so I'm going to discuss on Friday exactly how to install Linux in your computers, and I'm going to want that to be the main way that you interact with your program. Yes. And so on Wednesdays, we'll sort of discuss the very, very basics of writing our first programs. We're going to use a graphical interface called Scratch, and if any of you want to get a head start on that, scratch.mit.edu is the interface that we'll be using, and I'm going to go over on Wednesday a whole number of different programs that we can write using this very, very simple interface. And your first project will be to create a Scratch program due next week, but that will all be on Wednesday.